So just as a reminder, last week we saw a bit about fractals and patterns in general, well, self-recursive patterns. And we also mentioned a bit briefly the relationship to scale-free distributions and also information and semantics, meaning the meaning of information as opposed to syntaxes. Any questions from previous class? Okay. So today we will see a very brief introduction to networks and hypergraphs. They have become very popular in the last 25 years or a bit more because they're very natural ways of describing complex systems, nodes. Green lights. Yep. So networks can be useful to represent complex systems because if you remember, complex systems are characterized by interactions, and networks naturally represent nodes, elements as nodes and interactions as links. So they have become a very common tool for modeling complex systems. So we can start a bit with theory. We could say that it all started with graph theory. Leonard Euler was a precocious child. Legend says that he was like in his small school, not sitting still. So let's say it's trouble for the teacher. So the teacher told, okay, little Leonard, sit down and sum all the numbers from 1 to 100. And then Leonard sat, thought a bit, and then just came up with a solution. And the teacher was surprised, and he basically didn't do it manually, but discovered the formula for getting the sum of 1 to n. And then that n was 100, which I forget is like.
Is it Linear or Gauss?
Oh, I'm confusing. Yeah, it was Gauss, right? Yeah. Okay, so forget about that. Well, anyway.
I would rank him as maybe top 3 mathematicians.
Yes.
Excuse me, Professor, we're not getting any audio. Is it on? Sorry for the interruption.
No problem. Could be in a different channel. Works. Oh, the speakers are getting so.
Yeah, it's slow though. Testing. I just have to replace it. Let's just try this real quick.
Yep. I can do it. Okay.
Yeah, absolutely. Well, it's a little quirky, but yeah, it works. Not working too well. Yeah, if you hold it up higher, or if that one, yeah, that'll come on now.
Well, I don't know whether this one.
Yeah. Testing. Yeah, you just need to talk close to it. I have another microphone I can pair if you want to try it.
Sure.
I don't want to interrupt your class though. But it'll only take me about a minute to just pair it and try it to see if it's the microphone or if it's something else.
Sure, no
All
problem.
right, so I'll be back in about a minute.
Yep.
Thank you.
Yeah, so anyway, he was also a precocious child, and he was imported into the Russian Empire by Catherine the Great to make the textbooks for public schools. So one of my teachers told, no wonder Russians have good mathematicians. If your textbooks are made by Euler, then let's say it's easy to be a good mathematician. But anyway, in those years there was the problem of the bridges of Königsberg, now Kaliningrad. So then it was part of Prussia. Now it's part of Russia, and now there are more bridges, so that you can actually solve the problem. But back in those years, I think end of the 18th century, I think it's the river of Latva, or yeah, I forget which river is it. So downtown there are two islands, and there are these 7 bridges, as shown in the figure. And then there was this problem whether you could do a walk through all of them, but crossing them just once. So you can try, like, start with A, and then C, and then D, and then B, and then F. But then if you do E, then you cannot reach G, and vice versa. So Euler actually, yep.
We're gonna try it.
Yeah.
We just gotta get in the cabinet real quick.
So he actually defined graph theory to solve this problem. So representing as nodes each of the land masses, island or shores, and linked by the bridges. And then he showed that if you have a graph with more than one node with an uneven number of links, then you cannot have one of these walks. Let's call complete paths. Or I think they're called Euler paths. No? Because yeah. And also Immanuel Kant was living in Königsberg in those years, so we also had to not to bump into him. But anyway, about 100 years ago, Jacob Moreno was among other things a psychologist. He had this theory of psychodrama, which was anti-Freudian. And among other things that he proposed were these so-called sociograms, which we would just call social networks. And it was basically linking, let's say, students. I think these are linked by friendship. So in sociology, people were using this already since the 1930s. But this was more, let's say, a descriptive exercise, because, let's say, they were not doing much math on them, even when there was graph theory proposed by Euler and small advances by other mathematicians. And Pellerdash, he was the most prolific mathematician ever. Also, so he has highest number of publications, more than 1,000. Also a mathematician with most collaborators, also more than 1,000. Quite a character. So was Hungarian, and he used to travel with a suitcase and a plastic bag, and would arrive to some colleague's house, knock at the door, and just say, "My brain is open," and kind of settle himself in their house, expecting the wives to feed and wash his dirty socks, until either they would finish a paper or the wife would lose her patience and he would move into the next university town.
Real quick.
Sure.
Okay. Yeah, it's the room. It's not the microphone. It's the sound in the room.
Yep.
It needs to be turned up. Okay. All right. So even if the microphone, if you don't mind, continue doing what you're doing, it's the best we can get. I can call EdCom and they can come in and turn up the volume in the meantime. Okay. All right, Professor.
With this one?
Yeah, that one's fine. We tried this one. It's the same result. So it's something with the sound level.
Yep.
Okay. Thank you.
But now it's not working.
Testing. No, it's nothing.
Oh, no, it's working. This one?
Yeah,
But
you're getting
it
something.
seems it's even lower.
You see lower, yeah.
So you might know that there were many Hungarians working in Los Alamos in the Manhattan Project during the war, and there's this anecdote that he was in one of the famous restaurants in Santa Fe in New Mexico with Hungarian colleagues who were working in Los Alamos, and the Manhattan Project was top secret, but let's say many people knew about it, and they were speaking in Hungarian and in Magyar, and then he just switched to English and asked like very loudly, "So how's that bomb of yours coming?" Yeah. And also there's another anecdote. He was at some university and he was confused with a tramp, so the police stopped him because the way he was dressed or whatever, and they asked for an ID. He didn't have any ID. But then he kind of got off the hook because he carried one of his books and his picture was on the back. So he managed to convince the policeman that he was a professor and not homeless person trying to break into the maths building. Yeah. He also gave some prizes from his own money to solve problems that he couldn't solve, and he among the many contributions to mathematics he did, one is to random graphs in collaboration with Alfred Rengi, who has this phrase: "Mathematician is a machine for turning coffee into theorems." And let me open it logo because they have this. Well, NetLogo, even when it started as for agent-based modeling, actually they have the first conference this summer. So if you're interested, you can still submit. Oh no, no. Well, you can still go there. And okay. So in the models library, there's this whole section of networks. So this giant component, it's a very simple model that was studied by Erdos and Renyi. So you start with a certain number of nodes, and then you pick two nodes at random, and then you link them. And that's it. So imagine you have a heap of buttons, and then you pick two buttons, and you put a thread between them. Then you pick two more, and then you pick two more, and then you pick two more, and then you see that as you start, let's say you have just pairs or very small groups of nodes. And here the largest one, also known as the largest component or the giant component, is painted red. And then you just keep on doing this. And the size of the largest component is plotted here. And it kind of grows slowly. But then once you have components of medium size, suddenly there will be one link between components. So then the speed of the growth of the giant component is very quick. So, well, we'll just start adding more. So for example, we have here these two large components, and in a moment, the probability that they will join is increasing. So now they joined, and there was this big jump in the size of the largest component. And then you just continue. And once most nodes are in the giant component, the probability that the component will grow starts decreasing, because as you add more links, the probability that these links belong to, let's say, joins nodes that are already in the giant component are greater than having still isolated nodes in the giant component. So we have this sigmoid curve.
Hello,
Hello.
how's it going?
Oh.
Check, check, check. Check, check, check.
We're speaking about Hungarians, not about Czechs.
Should be good.
Thanks.
Yeah.
Okay, so then I'll just do this. Yeah. So probably you have heard about small world phenomena or small world networks. So on the left, there's Stanley Milgram, who was a psychologist, and at some point he was also interacting with Mandelbrot, who we mentioned last week. But he's well known for these obedience experiments, where people were told that they should put electroshocks to people that were giving the wrong answers. So it was like to test how far people would go. So yes. Sorry.
Are you?
No problem.
We owe you.
Let's see what's going on here.
I'm recording it on Zoom, so I can upload to the panel.
Perfect. That'll be perfect.
Okay.
Professor. Thank you.
Yep.
That's a great backup. Just happened this morning.
Yeah. Right, hello.
So there was this idea after the Second World War that the Nazis had been terrible, but that would never happen in the United States. Why?
Yes.
Because
I don't think it's this. It's
land of the free, home of the brave, whatever.
speakers.
But let's say from a scientific perspective, it's an interesting question. Not only whether that could happen in the United States, but why it happened in Germany. Let's say to understand the phenomena, and then how could that be prevented or its probability reduced. So
You can wear that if you want, but we have to come back and.
Yeah.
check that.
no problem. So these experiments were, I mean, that was the intention, to see how far people will go. And it seems that given the right conditions, the classic, I was just following orders, takes over, and most people would do terrible things. And later in the Phil Zimbardo's Stanford prison experiment, that was kind of confirmed, that he took Stanford students and put them in roles of prisoners and guards, and in less than a week they were taking their roles too seriously, and the experiment had to be stopped. And of course, those things wouldn't pass the ethics board nowadays, but anyway. Okay, going back to Stanley Milgram, another of his experiments was to try to see how connected people were. So it was in the late 60s, and he asked people from Omaha, Wichita, or some other city, and they were asked to send a letter to a target in Boston. Well, actually, most letters never reach their destination, so it's like, okay, we don't know that, but those that reach their destination, on average, it took 6 steps, because let's say they would send to somebody who might know somebody who knows that person, and then these were instructed to send that letter to another person, and then the target was reached on average on 6 steps. And actually, this phrase of 6 degrees was coined by Frigyes Karinci, another Hungarian, but let's say, I forget whether poet, yeah, I think a Hungarian poet, early in the 20th century. And this poem was precisely suggesting that if you take two people, I forget whether in a city or in the world, most probably they would be 6 degrees apart. Meaning that 1 degree is my friends, 2 degrees the friends of my friends, 3 degrees the friends of my friends of my friends. So anybody knows the guy on the right? Kevin Bacon. So he has been in lots of films, maybe no big roles, but and also I haven't seen most of his films, but for example in Flatliners well, anyway. So at some point, for whatever reason, some students started playing a game that it was similar to the Milgram's experiment, but with films. So somebody would say a film or a series, and I don't know, the series 24. And then you need to find a path to Kevin Bacon by film. So the degree 1 is actors who played in the same film or series or whatever. 2 degrees, the actors who played in a film, let's say 1 degree apart, and like that. So in case of 24, Kiefer Sutherland acts in there, and then he also acts in Flatliner, so it's just degree 1. Yeah. So or just linking actors via the films they appeared in. So yeah, you can calculate the Bacon number of any actor, which for actors it's not very interesting. But then the same mathematicians do with their Erdos number. So the co-authors of Erdos have Erdos number of 1, meaning if you wrote a paper with Erdos, then you are next to him. The co-authors of the co-authors of Erdos have number 2. So, and the co-authors of the co-authors of the co-authors number 3, and so on. So it's kind of a strange mathematical pride to have a low Erdos number, -4, which it's not low, but yeah, I'm not a mathematician, so anyway. Yeah, actually, at the last conference of complex systems, one of the invited speakers was Hungarian mathematician, co-author of Erdos. So we were like, we should publish a paper with him, and then we'll have Erdos number of 2, because of course he decides you cannot have Erdos number of 1 anymore. But and his co-authors, I think most of them also died already, so chances are running out to get a lower Erdos number. And then there are people who even calculate the Erdos-Bacon number, which is like the sum of both, because there are some mathematicians that have also appeared in films, and then you kind of calculate the distance to Kevin Bacon in films and Erdos in science, and you sum those numbers. And
so Erdos number is only significant after his existence. Like before his existence, no one has Erdos number.
no,
Yeah.
But I mean, of course, you can calculate with whoever, so you can calculate the Euler number. Yeah, and I think there's this math genealogy project, so it maps like who was PhD advisor of whom, and
Oh, yeah, everyone's like that.
yeah, and yeah, I think Euler is like in my in my advisor's tree somehow, but it's not that difficult. It's also like I know that many people, they can trace somehow to their ancestors to Queen Victoria, because she didn't need to have many kids, but let's say after a few generations, it's like thousands of people can, let's say, can be descendants of anyone. But anyway. Yeah, so with the popularization of what we call now social networks, Facebook and Twitter, these numbers went down. So actually, I don't know what would be the numbers nowadays, and also they might not be very meaningful because there are many accounts that are not active, and then there are many bots, and yeah, it would be perhaps more confusing to do the analysis now. But let's say in the early days, I think in Facebook was less than 4, and in Twitter, since it's directed, meaning that you can have some accounts with millions of followers, but in the early days, Facebook was non-directed, meaning that friends are friends. It's not that one is, let's say, somebody is my friend, but I'm not their friend. So let's say that limited the number of links per node, so that's reduced considerably the average path length. And speaking about average path length, yeah, well, let's better go to NetLogo. In 98, Duncan Watts and Steven Strogatz proposed a model of small world networks, and the way they defined them, or perhaps they were already defined, is networks that have relatively high clustering coefficients and relatively low average path length. So average path length means that you can get in few steps from any node to any node, and a random network like Erdos-Renyi networks have very low, well, relatively low average path length, because since there's no structure, the probability that reaching any node, it's very high. Of reaching many nodes, also because they have high connectivity usually. At least higher than a regular network. So this a regular network, let's say in this case, it's like a circle, but let's say also a grid would be a regular network, like a city. And if you want to go to the nearby nodes, it's short, but if you want to go all the way here, you need to go through many intermediate steps. So the average path length is higher than in a more connected network. However, the clustering coefficient, which is basically how many of your neighbors are neighbors, or how many of your friends are friends among themselves, which is something that is common in social networks, that you have communities, you have groups, and then everybody knows each other. And here you can see it. Usually, if you are sharing a class, you speak with people in the same class. So then if you make links of who you speak with, then usually many of the people you speak with, they also speak among themselves. So you have these communities. And that can be measured with this clustering coefficient, which is, again, the percentage of your neighbors that are neighbors among themselves. So regular networks have high clustering coefficients because, for example, this node, this neighbor has also these neighbors as nodes. This node has these neighbors as nodes. Let's say, this model of small world network starts with a regular network like this one, and then again you do random pick 2 nodes at once, or you can pick randomly one link joining 2 nodes, and then you rewire it. So for example, there was this link joining these 2 nodes, and now it links these 2 nodes. So that, let's say, removes some of the structure here, but then adds a shortcut between these 2 regions of the network. And as you add nodes, the average path length goes down very fast, but still most of the nodes have a high clustering coefficient. So with a few rewirings, the average path length goes down relatively quickly. And then when you keep on rewiring, the clustering coefficient goes down. And let's say the average path length doesn't go down anymore. And then you have more like a random network. So when you have this balance between regular and random, you have small worlds, and then these properties of high clustering coefficient and low average path length. And on Thursday, one of the papers we'll discuss is by Granovetter, perhaps one of the most cited papers in sociology, called Importance of Weak Ties. So again, here, if we have communities that have strong connections among them, then the so-called weak ties that link them, that link different communities become very relevant for different purposes. One, so that they are not isolated, but also for robustness, because if, let's say, something wrong happens here, the probability that it will spread to the rest of the network is lower if you have this structure as compared to this structure. So here, if you have a change here, it will propagate very quickly to the rest of the network. If you have a modular structure, probability that it will spread within the module or the community is high. The probability that it will propagate through all the network is relatively low. So that gives some robustness. And Herbert Simon, in the papers we discussed, already discussed the benefits of modularity and hierarchy and so on in complex systems. And Peter Chermely, another Hungarian, has a book about weak ties, and he kind of reviews in many different areas why these are relevant. So even more Hungarians, Laszlo Barabasi and Reka Albert proposed this model of preferential attachment, also known as the BA model, for scale-free networks. And oh, so you start with a node, and then you start adding nodes randomly, just like with the Erdos-Rangi networks. So you can assume that you have, let's say, all the buttons somewhere here. Then you start picking nodes at random. Then this random is biased, so you have a preference to attach to nodes that have more nodes or more links. So for example, this node has 4 links, this one has 2 links, and all the others have 1 link. So you basically divide the probability. So this will have like 0.5, no, how many links? 4. Yeah, so this would be like 4/10 probability that a new node will join this one, 2/10 that it will join this one, and 1/10 that it will join the 4 leaves. Yeah, leaves, it's, let's say, nodes with just 1 link. So yeah, again, it joined the central node most connections because it had the highest probability. And you just repeat this, and then you end up with a scale-free distribution. So in log-log, you have a straight line with steep of -1. So actually, a very similar model was proposed already by Herbert Simon in 1950s, but people didn't know about it until much later. So this is an illustration of the so-called Matthew effect, where the rich get richer. So again, this was described a bit by Pareto, late 19th century, describing wealth distribution, because this gives you power laws, just like wealth distributions. And I mean, different mechanisms can give you power law distributions, but this is one of them. It has some limitations. For example, there are no cycles. Since you are only adding nodes, not rewiring those that are already in the network, you don't have cycles, so it's like a tree. But then there are many modifications to this model. And also this model has been used for different purposes. So for example, a PhD student back in Mexico, he's finishing his thesis where he uses this preferential attachment to model star formation to reproduce the mass distribution of galaxies. So yeah, it's in a way a balance where you have few with a lot and a lot with a few. And yeah, so parallels have been found everywhere. Yeah, like I put this because even in comic books, some people did this social network of comics. I forget whether DC or Marvel universes, and they would link superheroes, or well, they would link characters if they appeared in a comic, and then turns out that you have few superheroes that appear, well, that they have many that appeared in comics with many other superheroes, but the majority appeared with just a few. And there are parallels in many different systems, not only networks. And in the 80s and 90s, when there was more and more data available, many papers were just like, hey, we have a power law. And in some cases, it's like, well, you really need to squint, like, or this city distribution is like, okay, just the tail is a power law, or this one, or I guess these are co-authors, citations. Wars is number of people killed in different wars. So you have few wars with lots of deaths and most wars with few deaths. Internet servers or pages, few servers with lots of traffic, most with not so much. Frequency of wars, so this would be Zipf's law, and so on. And there has been lots of debates about whether these distributions are really power laws or not, but it doesn't really matter. The important thing is that when you have this type of distributions, calculus doesn't work because you have the fundamental theorem of calculus requires that you have a distribution with a well-defined mean, and these don't have well-defined means. I mean, you can calculate it, but it doesn't tell you much. So for example, in earthquakes, do we have earthquakes here? Not here, but yeah, or solar flares or market crashes. We don't care about what's the average earthquake frequency or intensity. We want the outlier. Same for market crashes. So yeah, okay. We don't have like a calculus for this type of distributions. We're still kind of trying to figure out how to deal with this phenomena. And actually, it's a consequence of complexity to have this type of distributions, because when you have few interactions, that usually leads to additive processes, meaning that you have change in your system, but then because there are a few interactions, that change doesn't propagate through the network. So a change in one element does not change other elements, and then the variables kind of have a mean value, and then that gives you a nice distribution. Gaussian, Poisson, doesn't need to be symmetric, or could be beta distribution and so on, but let's say you can do calculus. And there are outliers, but in most cases you can ignore those extreme cases. But then when you have more interactions, when there is one element changing their value, I mean, I move like this, like a change value in the x-axis, or then that will move the values of others. So then you end up with multiplicative processes, and then you end up with scale-free like distributions. Now, when you have too many interactions, then whatever you touch, everything will change, and then you end up with something like white noise. So then again, there you can average, because you don't have a well-defined mean, but then you have like a uniform distribution. And then you can do statistical mechanics and like in thermodynamics, and then you can simplify. But in this intermediate case, which we call complexity, where we have an intermediate number of interactions, details matter, because you don't know whether, so for example, this is the passenger airport network. So you have a few airports with lots of flights and most airports with few flights. So here it matters which airport is which, because it's not the same if one of these closes down, then this should be Atlanta or Heathrow or Charles de Gaulle. They have very different effects. So here details matter, and then we cannot simplify, and then we need more information, and then that limits prediction, and there are many different implications for this. Another property of these scale-free networks is that they're robust to random attacks, because random attack most probably will land into a non-relevant node, like one of the many small airports, so it doesn't affect the network gravely, but they're fragile to directed attacks. So if you had to choose one airport and then you choose one of the 10 largest ones, then you disrupt the whole global air traffic. There are ways of making these type of networks more robust, like you link all the major hubs, as the airline network is linked. So it is not that, okay, when Heathrow is closed for whatever reason, it's a big chaos, but let's say still there is traffic through other airports, so people can find alternatives. Like I don't know, for example, a few weeks ago, Lufthansa was going on strike. So it's like, okay, no flights to Germany, but then there are many different routes to go anywhere in Europe. So not through Munich, not to Frankfurt, but then you can fly through Amsterdam, you can fly through London, you can fly through Paris, you can fly through Madrid, and many other airports. So let's say people can still reach their destination. People have been studying temporal networks, which is basically how different networks change in time. So, for example, this is a social network, but then different people, let's say, speak or interact with each other at different times, could be different days or different hours, and then that network changes. So this could be different temporal layers of the network. one classic data set to study temporal networks is the Enron email data set. You're too young to remember this, but I don't know. I think it was around the year 2000 with Enron. Well, there was this big company that made lots of money in not so legal ways. So there was a big legal process. And as part of that process, all the emails of the company went public. So we have that data sets like 2 years, and then we can see who emailed whom. And then you can see that every day you have like a scale-free like distribution with few people sending many emails and most people sending few emails, also for receiving. But you see that every day the hubs change. So the person who's sending most mails is not the same every day and throughout the whole history of the dataset. So, I mean, there has been some work, and more generally, here each layer represents one time slice, but more generally, we have multiplex networks where each layer can represent different aspects of a network. So this, for example, multi-layer of a transportation system in a city. So you have the street network, and another layer, maybe the bus network, another layer, maybe the rail network, or metro network. And then this can have different connections. So in order to move yourself in a city like this one, you can go through the streets, but then you can go into a station and take the bus or the metro, and let's say like that you can navigate. So many algorithms that were originally developed for networks have been extended to multiplex networks, like find the shortest path. I mean, it's not that different. You just explore, let's say, multiple layers instead of just one layer. Can you think of other examples of multiplex networks? Well, the thing is that you can link people almost by any property. So the classic ones are like, for example, co-authors, but then you can link people also by what kind of music they like or soccer team they favor. And then if you like the same, you just link them, and then you can have different layers of different aspects and then see whether they're similar or not. And it's interesting because it kind of highlights the diversity of people in the sense that we have, for example, this idea of, just to give an example of United States, that there's like right wing and left wing, and that's it. And then the right wing are with guns and anti-immigration and racist and anti-abortion and, well, many different pro-Trump. And then the left wings are woke and pro-abortion and anti-war and vegetarians and so I mean many cliches that kind of permeate. But then when you analyze these details, you see that, for example, if you look at people liking music or art or different sports, there's like completely different divisions of society. Yeah, so I can imagine that if you go to a baseball match, there would be, let's say, the division of who is cheering for which team. It's very different from political views or music preferences or food preferences or ethnicity or language or whatever. Yeah. Another example would be all the different variety of social networks that we have, like have Facebook and LinkedIn and X and Blue Sky and MySpace still exists. And so on. Mastodon And of course, some people don't have nodes in all of those networks. Just like here, you don't have bus stops in every corner or metro stops, but still you can calculate how people are connected in different ways. And the fact that people are connected that in many different layers doesn't necessarily mean that they are closer, because it could be just that some people don't have profiles in many layers, in many social networks. So yeah, in all of these, the data can be extremely biased. I mean, the heydays of Twitter, when many social scientists were taking that data to do all sorts of studies, which was never before possible. It was great, but we were all aware that people using Twitter was just a particular part of the population, especially worldwide. But still, I mean, many interesting things could be done with that. And another extension are hypergraphs. So networks are basically linking two nodes, but then we could have so-called higher order relations. And this can be of different types. So for example, here, say these are two nodes, but then we have a relationship between these three nodes and then these three nodes. And then the way of representing them is more problematic. They're still not used because in some cases, network representation or a graph representation is enough. So instead of having this representation with three nodes, then you connect these two, and then you connect these two, and then you connect these two. And then you say, oh, it's the same. At the end, it's just representations. And then there's still a debate like, okay, in these cases, it's not the same. And then you don't get the same if you do the network representation of a hypergraph. But so far, what I've seen is that the increased complexity of hypergraphs is not justified in the sense that you don't get completely different results than you will get with normal networks. So people have been still using networks. There have been many extensions of, again, algorithms or networks to hypergraphs, but it's still not so used. Just to
But I guess similar to the multi-layer network, each part can be represented in the name. And what's the difference? Yeah.
So multi-layer networks, you are one link will link just two nodes, either in the same layer or among layers. And in hypergraphs, a link would grab more than two nodes, and it would be a relationship between more than two nodes. So for example, you can build a network of classes in SSIE, and then you link students if they share a class. And that gives you a representation, and then you have one node per student, and then you can have many connections. But just like that, you don't know exactly how many classes are shared by different students. You could do a weighted network, and then you say, okay, you label each link with the number of classes that are shared by students. So if you share two classes with one student, then you put two, three classes, three, and so on. But another way of representing the same relations is that you just put like one link for all the students per class. So again, you have the same number of students, but you have much less links. You have just one link per class, but then each link kind of contains everyone. And whether that's easier or not, it depends. And whether you are losing more information with one or the other, it also depends on what information you
So on each part, there are no links between those Oh, definitely.
Mhm. Yeah, I mean, this is just an arbitrary example. Yeah, V4 would have like a self-link, but here it's just represented like a blob, and V7 doesn't have links.
But if you have that would be, that's like having for each.
Edge.
Is that right?
Yeah, so here they call edges what I'm referring to as links. And traditionally, edges link two nodes. And if you allow self-links, then it would be just one node linked to itself. But let's say, and then in directed graphs, then you have like a source and a sink, or a input and output, or output input, let's say the direction of the link. And you can also have directed hypergraphs, but then you have like many sources and just one link. So for example, it could be that V1 and V2 go to V3. But then you could say, oh, well, I just draw two arrows, one from V2 to V3 and another from V1 to V2, to V1 to V3. And in some cases it's the same, and in some cases it's not the same. Because it would be, so for example, if you care about the difference, whether you have and or here, then it makes a difference. If you don't care about the difference, then it doesn't make a difference. And in some cases, it also depends on what's not only the topology of the network, but what's the functions. For example, in random Boolean networks, since you have Boolean functions of the inputs, then you can easily do whatever logic function of the inputs. So then you can represent easily this in any complicated relationship between inputs and outputs. So again, networks are useful to represent complex systems. Nodes represent objects, linked interactions. Shows that topology matters. Before, it was common to use so-called mean field approach. So you would just average. But then we saw, like, for example, in the small world networks, if you take average number of nodes, that doesn't change. But then the organization changes, and then you get very different properties. So in many social systems, let's say even when you have the same number of nodes, same number of links, which would mean that your average numbers don't matter, the organization matters, and that gives you very different functions. And then there are many different flavors, many applications. The 20th edition of the Network Science Conference will be this June in Boston. And to celebrate, they have some interesting joint keynote lectures by Watts and Strogatz and by Barbash and Albert. So some of us will be there, looking forward to see how it goes. And yeah, it's quite an active field. Many people here in SSIE are working on networks. Last December was network conference here. And yeah, there's many things to do. They seem to be very useful and exciting times. Any question? Oops.
Yes, is it possible to have multi-dimensional graphs in the sense that most of the graphs are 2D and brought on a plane, even 3D if you have like a visual of it. So is there a concept of multi-dimensional and how do we analyze it?
Yes, so networks themselves don't have a dimension. How we plot them is what has dimensions. So for example, this network, we can plot it in any dimensions we want. And then the question is how cluttered it will look. And in some cases, you would like to have more dimensions so that, let's say, edges don't kind of cross in their projection. But for the network itself, they don't care. You could calculate, let's say, precisely which dimension would be required to have these non-crossing links, but it's not relevant because it's like when you have a phase space and you have multiple dimensions. If you want to plot it, then you care because you need to draw it. But if you are just doing analysis, then it doesn't matter how many dimensions you have, you just take them as vectors. So it's the same with networks. They don't have a, well, we usually don't care about their dimensionality, which is something, again, you can calculate, but that doesn't matter that much. Any other question? Okay, so Thursday we'll discuss these three papers. Schelling is classic dynamic modes of segregation. Mentioned the strength of weak ties, which is sociology, but also early network science. And paper about cybernetic cities. So for next week, please upload one page with advances and preliminary results. If you have figures, please figures, share in discussion. So just one member of the team to upload, but then all members of the team, please comment on other projects for feedback. So the idea is that, I mean, there's less than a month until the end of the semester. You should ideally have already preliminary results. And if not, at least a well-defined problem and, let's say, not only what you want to do, but you should have already started doing that. Yeah, because there's not much time left. And next week I'll be at a conference in Morocco, so Hiroki Sayama will be guest lecturing again. It is from April 1st. So see you on Thursday, but next week Hiroki will be here Tuesday and Thursday. Any other question? Okay.